Well, as you can see, when the x-axis and y-axis return to the mechanical origin. In fact, this mechanical origin, there is no limit switch. How does it know? It has already hit this limit position. It is the motor's function of zeroing without sensing. When the motor detects resistance is greater than its normal running resistance, it thinks it has hit the limit switch. At this time, we give the host a response. Then the host computer, it thinks we hit the limit switch. Then it sends a coordinate to find the coordinates of the mark point, and then find the mark point. Let me show you again. This kind of zero-sense homing technology is widely used in 3D printers. This technology, since it detects the running resistance, it has certain requirements for the tension of the belt. Has certain requirements. If the belt is too tight, it may not be able to move at the beginning. When it starts, it feels the resistance is too high. It will stop. It will directly look for this point. It definitely won't be accurate. If the belt is too loose, when it hits the mechanical limit, the belt is too loose. It doesn't give enough rigidity. He felt that the resistance was not enough. So it keeps walking. It will keep hitting the machine continuously. And if the belt is adjusted too loosely, it will also cause a loose timing belt will cause excessive backlash. If it's too tight, it's easy to lose steps. So, adjusting the timing belt is a subjective process. I say you tighten it a little bit, but some people may tighten it too much. If I say loosen it a little, some people will adjust it very loose. So, we now randomly include a tension meter to measure the tension of the synchronous belt. The tension of the synchronous belt. So how do we measure it? We will take the x-axis as an example. And we're going to start by moving the header to the edge. Turn off the machine. Move it to the edge. Then we hook the dynamometer. Hook it to the middle. Hook it to the middle of the belt. Then pull it. Then pull it to the torque scale. I can't handle it with one hand. Just pull it in parallel. It should be said that this pulling direction is perpendicular to the belt. The timing belt is vertical until the torque is 10 Newton meters, which is the maximum range. If these two synchronous belts, the two synchronous belts can just touch each other, then it's suitable. Look, I pull it over here, and they touch each other, then it's suitable. Yes, if they can't touch each other. You've pulled it to 10 newtons. They can't meet yet. It's too tight. If they touch together before you reach 10 newtons, it's too loose. This adjustment is adjusted by pushing the screw. Right. You can adjust it by screwing the screw and check the feedback words at the same time until it's just right. Then fix the 4 screws. And it's done. And the same goes for the y-axis. When measuring the y-axis, when you measure, you also need to move the module to the edge first. Then pull it. And pull its middle part. That is to say, when we measure this thing, not only to, in order to accurately achieve this non-sensory zeroing, but also to minimize the hysteresis. Because if it's too tight or too loose, the backlash will be large. If you are too tight, it will cause the robot to lose steps, which also leads to excessive backlash.